Okay. So good morning, everyone. And as already introduced, we are from ABB. And yeah, we're going to take you through what we have been doing with our Edge software platform using Red Hat technologies. And this is a brief agenda. I mean, what we're going to talk about. We'll very quickly go to what is ABB, what is we are doing to accelerate innovation, and what kind of digital habitat we are creating, where we are using the technologies more intensively. And we'll go through this Bootsy, use how we are using Bootsy, and a couple of real application use cases, which we are enabling for our customers in production. So that's what we want to do. I'm Vikas Maurya. I'm a product line manager for our software platform in industry. And I have my colleague Anders. He's our chief software architect for the same software we are building here. And so we start with this. So we have ABB is working primarily into electrification and automation technology provider for industries like electrification, robotics, and discrete automation. We have process automation and motion. These are four business areas. And we are headquartered in Zurich. We have more than 105,000 employees, and we are over 100 countries. And we are close to 140-year-old company as well. So it's a long history. But we are, in particular, working in process automation domain. And that's the business area we are serving with our DCS technologies. And what we have today, I mean, we have been serving from decades to our customers. But since we have going through all this digital transformation, our customers are going through the digital transformation journey and what they're expecting. So I'll try to explain this into the four bullets here: situation, challenge, and what is our vision and the value we deliver. So what is happening now for us is that our industries, our customers are expecting big gain with all the digital technologies which is on the shelf, like edge, cloud, everything it is going on. And we have this, every big customers we have is going through their digital transformation journey. And that is what we have to also kind of be part of it and make sure that we can serve our customer in their digital transformation journey. The biggest challenge which we have is that our customers are running critical plants, and plants means you have power generation plant, oil and gas refinery plant, and that is the technology we are providing to automate the whole plant, and that is running really critical operations. And if we introduce a digital technology into that kind of a system, it might disrupt their plant operations, and that's what we want to avoid. So the main challenge we have that we want to adopt digital technologies, digital transformation, but without disrupting the plant operations. So that's the big thing what we are trying to solve. And our vision is to kind of provide a full-scale digital ecosystem for our customers where they can actually play with the technology, they can bring applications to optimize their plant, bring the sustainability application, decarbonize their plant. I think these kind of things what we are trying to enable, and that is the vision we have. And the value is really the risk-free digital automation. That's what we are offering to our customers. And when we build this, we have to build this very carefully. And when we do this, we have to do this something like this. So this picture explains how we are trying to bring something called digital habitat into our automation systems. So on the right side, you see that there is our core process control technologies, which we have provided to automate the plants till today. And we are trying to build, on the left side, if you see, digital habitat providing an edge and cloud deployments. And that is connected to our DCS system, where we are safely and securely extracting the process data, which is available into our DCS systems. And using that process data, this digital habitat where these applications can live and deliver values, they might also require to write back to the core process control. And what I mean is, like, if we have calculated an optimal set point using the, let's say, AI/ML technologies, and it says using this set point, you can optimize the production of your plant, then that set point need to also go back to the control system to change the value which is running on the controllers, for example. And that also we have to take care. So taking out the data and also sending back the control to the plant. And that's what this digital habitat we have created. If you look at where the edge is there, that's where primarily we are using Red Hat technologies. We have started to use this Red Hat OpenShift there. And then we also moved recently to Red Hat Device Edge, which has Microshift and RHEL as a package coming from Red Hat. And that's where we have enlarged things. And we are using certain things into that, which is like Bootsy and all. And I just then to Anders to explain how this is used inside this. So Anders, take it.
Yes. So let me set a bit the context as well. So this control system on the right, that's running in OT space, like closed environment. And then we have these red boxes, kind of firewalls between the IT side of this. So where we deploy Edgenius. So this IT environment, but it's very close to the OT. So we deploy this environment and we want to manage it like an appliance in the sense that you can install it, you can add applications to it, and you can update it. And the whole system is managed like a single thing. And of course, we have a couple of different variants of this product. Like we have one which is cloud managed, where we have agents running in the cloud, or software running in the cloud and agents running on the edge, defining what to deploy. And we have another version where we're running this with air-gapped environment. We define everything locally. And in both versions, we run the same set of applications and containerized deployments. And of course, they need to be working in the same way. We need a consistent environment. So what we have done then, if you click, is to switch to something called Red Hat Image Mode and Bootsy technology. This allows us to build the operating system image, kind of like how we build containers. So we build like a base operating system where we include Red Hat Linux, we include Microshift and the Kubernetes plugins. We put the OpenTelemetry collector and also some installation framework. And we put some core services in. And we build this and push this to our container register. So this becomes our base operating system binary image. And then we build the different product variants using this as our base, kind of like if you build containers apps, we have a base image. This is kind of our UBI for the operating system. And then we add the additional layers on this, where we add this version or variant-specific software. And again, push this to our container register. So now we have different images of this that we can use to deploy. What we then do is we use the Red Hat image builder and build installation versions of this. We can build Anaconda ISO that can be used to install this on bare metal. We can build a virtual hard drive image that we can load into a virtualization environment, which contains then the whole full stack. So this gives us a consistent set of artifacts that we know they are the same in all product versions and variants. We get some additional benefits too. So when we apply updates, it works similar to how container updates work, that it transfer modified layers to the target system. And that lowers our network load and the effort to transfer updates to this. It can kind of be important since sometimes we are in air-gapped environment and it could be quite far out in nowhere as well. The other big advantage is that when we update the operating system, we get this atomic behavior that we know from container updates, that we can transfer the new version, we can restart the system on the new image version and keep running. And if it for some reason doesn't really work, we can also roll back and go back to the previous version. So we get a very nice, robust system with this. And this is really cool stuff, pretty new stuff as well.
Moving forward, moving forward. And we have two application use cases. As I said, the first use case we're going to talk about is what we call augmented operator. And this is just to kind of explain the context, what is an augmented operator and why we work on this use case. So we have some concept on this human analogy, right? So we are humans, and we have certain skills. So we have like intuition, creativity, expertise. That is the human capability, but computation is not, right? And there is an artificial intelligence which is coming, which is basically based on knowledge learned from data, right? So they are built from knowledge which is generated by experts or by data and everything in the past. And they are also kind of generates expertise, and the computation capability is immense there, which is not there with the humans. What we are trying to do is amplifying the human potential, right? So we want to augment the humans having an additional capability added through the artificial intelligence. So we want to do is like augmenting the human by adding the artificial intelligence use case, or providing this additional information to them. So that's the kind of thing. And then we have two personas, which is control room operators and process engineers. These are the two humans we are talking about who need to be kind of, or we are aiming to augment them with additional capability. So what is control room operator? Is the control room operator is the person sitting inside an operator room, looking at the very big screens and trying to monitor the whole plant. So if the plant is running fully automated and anything goes bad into the plant, there's an alarm getting triggered or something goes bad. This guy is sitting 8-hour shift all the time looking at the screen. If something goes bad, then he has to act. So there's a lot of cognitive load on this person. And then this process engineer is the guy who has a expertise knowledge of the process. For example, power generation process, or is it an oil and gas refinery? So there's an expert who knows the process, who can see the data and understand how to optimize the plant for better production or reducing things. So there's two people, two human in the loop who are working in the plants, looking at our DCS systems day in, day out. And they need to be helped. And it's the same kind of concept, like getting assistance for them. So we have like cars, right? You drive car, and they have to always be looking at the road if what is coming, what is not coming. But they can be assisted by providing additional information. And the same thing we're trying to do for these two personas we are talking about, the operator and the process engineer, that you have to do your job anyway, but like in car, you get additional dashboards with more data about your car and things like this. And that's what we want to offer these two personas. So how do we do this? You see this is in a loop in the middle. So control room operators are monitoring. They're identifying any problems in the plant, and they interpret and act on it. So that's like their daily job. But the process engineers is what they're analyzing what has happened and how to solve that problem for the future. And then this is the loop. We try to kind of bridge this loop and help them doing this job. And I just let Anders then to kind of more talk about how this is being implemented, our augmented operator use case, which helps to kind of allow these people to analyze the situation better, predict things better.
Yeah, so this control room operator, he's using his operator station. And you see this graphical display, like that's depicting the state of the plant. So when we implement like this augmentation support, he's still using the same things. It's just that we're putting more situation awareness. We are highlighting more things. We are giving him more information in this environment. So he can understand that there is something going on. And if I want to solve it, this is how I would do it. If I do not solve it, this is what might happen. So he gets help and assist on how to run and solve situations when they actually happen, pretty much in real time. And this other guy, this process engineer, he's more like in the office environment. So he's doing like more like a desktop job. And he wants, of course, the same data. So when he should analyze something, he needs access to huge amount of data. And to be able to analyze this, figure out what's going wrong, create a trigger for how to detect when this happens next time, and put in some information about how to deal with it. So that when it happens the next time, the system can automatically detect and present to the operator, here's what you should do. So this is kind of what they're doing with these applications. And this is then how it works a bit. So we have to the right, again, this control room, the operator stations and so on. This is in one security zone. Then to the, well, more in the middle, we have the edge running this software. And to the right, we have the process engineer in the office environment. So data flows like this, that the control system is continuously monitoring the plant, collecting data. And we are streaming that into the edge. We're also streaming the information model of the plant, like a knowledge graph of how is objects related, how are things related, what are the types of objects, what metadata do we have. We put all that into this edge data platform in the middle where it is available. And then we run applications that are monitoring the current values as they change. And when something is detected, they also query historical data to figure out what to do. They pick up this data from the system and annotate back into the operator environment where we are presenting these views, annotating the actual operating stations. The process engineer, of course, he's more like feeding information into the system as it happens. So to make this work, we need to process a lot of data, and that's where we need to use GPUs for this. So we run this on Microshift and on RHEL, as we discussed earlier, and on this we install the NVIDIA driver stack. And we install the NVIDIA device plugin, and then we can allocate GPU to our deployments. And this is a very static deployment. We know what applications we are running. It's not that there are 100 data scientists deploying anything. This is sitting there all the time. So we can statically allocate, like these applications are going to use these GPUs. And by using the GPU, we go from response time on seconds to milliseconds. And in this world, like that's the whole enabler to make this actually work.
So the next use case which we would like to talk about is the predictive maintenance. And this is just to kind of start, as we talked about operators and plant and all. So predictive maintenance, what is the situation we have today in the plant, right? So plant is running, your stuff is going on, and suddenly like 2 o'clock in the night, the guy, the maintenance guy who's sleeping gets a call, right? Saying that, hey, something has gone wrong, production has just stopped dead, and there's some major asset, which is like heat exchanger or something, they just got overheated, and it's just kind of stopped, right? So the production just stopped. And the reason is like very unclear. Maybe this is just the backup fan which has failed, and that has led to kind of overheating of the heat exchanger or some major equipment, and production has just stopped, right? And what happens with this kind of situation is that your revenue and production losses will start because you just went into a downtime which was not planned. And then if such instance happens, there's also like safety risk. So if something blows up and there are people around, I mean, there's definitely it's a very dangerous situation. And once we have to kind of do this fixing of all these equipments more in reactive mode, and it's very expensive for our customers, right? So this is the situation today, which we are trying to solve. So what our customer says, this is not acceptable. We can't work like this. We cannot live like this. We need to see better. We need to foresee more, and we need to optimize everything. And that's what our customer is actually looking for. If you need to see better, that means that unplanned maintenance time would actually go down at least 4 to 10 times than what we have today. And for that, you need like 24/7 real-time performance monitoring applications with pre-built models and which can calculate, which can understand and figure it out. So it is like just a monitoring of performance, and you continue to just check what is happening, and if some kind of warning comes, you act on it. But then there is also this possibility to kind of foresee better, right? So you can even predict issues using AI models built with real-time operational data. So you can predict, oh, it's not failing today, but it might fail next month, because given the lifetime available for your equipment, it says that lifetime will be completely consumed next month. So, and you need to probably plan the maintenance according to that. And the next is like, can we then, when looking at the data, can we simply optimize everything? Can I see when it will be failing so I can optimize my maintenance schedules? And this will additionally help us to reduce the cost for the customer for operating things. So these are, let's say, desired customer experience. That's what we try to offer. And what we have is APM Predict Electrical. It's an asset performance management software, which is running on Edgenius, which is our software platform, as I said. And this is one of the project which we have delivered in Europe. This is in Netherlands. It's in a European refinery, where we are doing the electrical condition monitoring. That means there are equipments like switch gears and IEDs and all, which is data being collected and monitored at the edge. And customer has selected this offering just to ensure there is a better predictive maintenance they can do. And this project is today commissioned and is running in production. And how does it there? You see that there's two devices on the south side collecting the data to Edgenius. The application is consuming the data directly, running on the edge itself, and it has, of course, the cloud connectivity for managing the software and things like this. But this is one of use case, one of the real project we have deployed here in Europe using this technology. So the architecture, I mean, Anders can explain the architecture, how we
so again, we have a bit the same thing. Here we have some more networks and things. So if you start from the bottom, we have various field devices and sensors and PLCs and so on, and we have control systems. And what we do is we collect data from these, but they are in a different security zone typically, like we have edge on a higher level. So what we do whenever possible, we put in something which can stream the data from below to up, like using MQTT as a carrier protocol whenever possible. Otherwise, if not possible, using gateways, which do make it possible. But that brings the data into the platform. And the thing that integrates it into the platform is this thing that says connect. Those are deployed services that are transforming this data stream, putting it into this edge platform in the middle, making it available for applications. Then the applications are similar to previously use case. They are processing data concurrent as data is coming on a data exchange. And if they do detect something, they can also go and use historical data to use that. And then they are outputting the result back into this Edgenius platform, into the same context as where the data lives. And that means we can use presentation software like dashboarding to query the system, to understand the current state, to understand the health of these assets in combination with the process and so on, and then we can present this to our users. So they can see the state of the whole assets in their system in kind of real-time live.
Thank you. So the first question is supply chain security. Basically, how do you attestate your AI solution not to be tampered with? Because that would be a great place to plan something, and I would guess that for most of your team it would be extremely hard, if not impossible, to discover it. That's one thing. The other is, how do you do lifecycle management on the edge, where your clients do not want to update to every version? So you're basically doing waterfall style of lifecycle management. Thank you.
Okay, maybe I take the first lifecycle management question. So this is the, let's say, very, very, very important and hot topic for the kind of industry we serve, because we can't go for a very fast life cycle. That has not been the practice. We had been always on a kind of LTS versions of our software and tried to support them as long as possible. With the technology switch, especially on the edge and digital technology we are talking here, of course, this is going to be faster. And we are using, I think Vodafone presentation also, they said they are using the LTS version from OpenShift, and that's exactly what we are also doing. And EUS line, where we have this 4.16, 4.18 versions, which has a longer support. We at least get like 24 months there. As a 6 months active, and like another, I think, 18 months is more maintenance support. So at least we got 24 months to kind of keep the customer on the same version. Yeah, but it's challenging. But one thing also which is pretty dominant in our industry is there is a huge awareness on the security patches. So we have even regulations coming in Europe talking about taking care of security patch updates. So that anyway gives us the window of opportunity to kind of go and update the system. And that is a good vehicle to convince customers that you need to update your system, because you today even our DCS systems, also the software we are deploying patches quarterly more or less. So that is the same argument we are taking, that you have to update this system anyway. And in this case, you are of course moving the version. That is the vehicle to kind of convince and talk to the customer, convince and go on that one. The second question you said on the
Maybe I should take. So how do we handle the supply chain and so on? So since we build this as an embedded system in a way, like we provide the stack, we can also sign and scan, of course, in our pipelines, but we are building, but then we also sign everything we ship, and we apply signing verification as well. We do not allow running unsigned things on these environments. That's a way to do it. We're still lacking some things in the boot C, so it would be nice if we could tie up the boot C to secure boot and also have that there. I think there is still something that could be enhanced there. That's kind of what we do.
Yeah, I mean, I think on the AI models, of course, there are more things, and it's still new for us, so we are still learning and adapting. I can say we can't say that we have solved everything, but it's the area we will, of course, figure out more.